Minasan konnichiwa. My name is Tonghui, and I'm a tech lead on the backend team. And today I will talk about how we migrate our backend API from a monolithic design to a microservice design. So if you have attended the previous talk, you probably already have a good idea of what kind of platform we've built to run microservices. And in this talk, I'm going to focus on how we actually develop the services for our backend API. So let's start from the background. Nowadays, we kind of all agree that we should, design the backend with a microservice design. But we didn't start that way, because when we started Mercari about 5 years ago, we had only one backend API. It was single repository and deployed as one web application, which is, understandable because at the time we were small enough, and as a startup, we want to move fast and want to ship features as quickly as possible. So as a product, we provide, iOS clients, Android clients, and the web interface, and all of them just talk to this backend API through HTTP request. And then we also have some internal tools, which is used for internal admin purpose, and they also talk to this API through HTTP. So this is about it, and we moved fast on this. In the last 5 years, we actually added more and more features to this, and as you can imagine, this backend API has become much bigger. And as of earlier this year, it has evolved into a code base of about 500,000 lines of code with over 100 contributors, and on average, we are submitting about 100 pull requests every week. And we are still growing. We want to become an engineering organization of about 1,000 engineers. So if you try to imagine 1,000 engineers trying to work on the same repository, trying to ship features without breaking each other's code, that's going to be very difficult, if not impossible at all. So that's when we decided to do microservices. But question is, how? How do we actually migrate the backend from a monolithic design to a microservice design? So I want to explain this in mainly 2 ways. The first is, how do we implement a new feature in microservice? And then, how do we break down the existing API into multiple microservices? Let's start from the new feature. Let's first simplify our current scenario. Let's say all the clients talk to our current API like this, and let's say we want to make new feature X and Y. And a very straightforward idea would be, just implement these new services, deploy them, and change our clients to talk to these services directly. So if you keep doing this, you will soon realize that a lot of the work will be actually repeated in both the backend API and the new services. For example, they may all have very similar code to bootstrap the application, take care of user authorization, and etc. And that's why we introduced the API gateway. This is a common pattern in a microservice design. Basically, we try to put our backend behind a gateway and let the clients only talk to the gateway. So for each request, the gateway will take care of the common work of, for example, SSL termination, DDoS protection, authorization, authentication, and then route each of the requests to each service to actually serve the request. That's basically the brief idea of how to add a new service. But also, I'd like to take a deeper look at the actual technology, the actual technologies we use to build these services. For the existing API, it's deployed in a data center called Sakura. If you don't know, it is a traditional data center in Hokkaido and providing mainly bare metal as a service. And for the new services, we deploy them to GCP. And more specifically, we're trying to use JKE so that we can use Kubernetes features like service discovery, load balancing, auto-scaling, etc. The existing API has been mainly used in MySQL as the backend storage, but for the new services, it's actually up to each service to decide what to use. And because we're using GCP, most of them end up using managed databases like Cloud SQL or SpannerDB. The clients still talk to our API gateway through HTTP, but for these new services, they actually send the serialized protobuffer messages in the request body. And when gateway gets the request, it will deserialize the message into protobuffer messages and then call each service with gRPC. Most of the services, including the gateway, has been implemented in Golang, but because we are using gRPC, we are actually free to choose any other programming language as long as it has good gRPC support. That's roughly the technical stack we use. And next, I'd like to step into how do we break down the existing API. We still need to do this because, as we said, this API has already been too big to scale. And even worse, when we add new service, we often still need to depend on the existing service because most of the major functions are still in there. So how do we split it? And honestly, this has been a very hard question for me for a long time. It's just too big, and I don't even know where to get started. So imagine this if you're facing like 500,000 lines of code, and you're supposed to, decouple this into tens of services. Where do we start? And I was like, okay, let's try to look at what's in there. Let's start from the UX features. And let's take a look at what are the features that we provide to our users. From the user perspective, this is what we provide. We allow them to log in, sell something, and then some other user may just come and search for something, buy something, and if something is bought, we allow the seller to ship it to the buyer. And then we analyze each feature and try to find out what are the fundamental components that power these features. For example, for the sell function, we will need the user component because users need to be logged in before they sell. And we also need the item component. And by the way, item is something we sell in Mercari. So obviously, we need the item service to support that. And then also, we need the photo service because when they sell something, we allow them to take a photo of that item. And for another example, let's say shipping. For shipping, we obviously need to know, who we're shipping to. So we need to know the user. And we also need to know what we're shipping. So we need to know the item. And we also need to know, the address of the user because, that's where we're shipping the item to. And then with all this information, we try to split them into services. And basically, what we do is to, list out the necessary features and list out the necessary functions. And try to find out what are necessary for what feature. So by doing this, we're kind of splitting the system into two layers. The first is kind of the user-facing layer, and we call them the BFF layer. And BFF is short for backend for front-end because it's kind of user-facing, providing direct user interface to our clients. And then the next layer is the DO layer. This is where we actually define our data models and handle data storages. And for each DO service, they are responsible for their own data storages, which in other words means, by splitting the service, we are actually also splitting the databases because each database is going with its own service. And this is essentially the service mesh graph. And of course, this is very much simplified for the presentation purpose. And in reality, it will usually look like something like this. Those are service mesh graphs from Amazon and Netflix. Of course, we are much smaller than these companies, but eventually the service mesh graph will grow into something like this. So that's basically the general process of how we break down our API. And to kind of summarize, to migrate to a microservice design, we mainly talk about how to implement new feature and how to break down existing API. For the new feature, we mainly focused on the architecture design, the gateway pattern, and also the technologies we introduce to power these features. For example, Kubernetes, Golang, gRPC. And for breaking down the existing API, we mainly talk about the process we went through. Basically, we start from the front-end features, and then we analyze the fundamental components that power these features, and we try to split them into services and draw the relationships between different services. And then the next job is to, actually develop the services, run them, test them, and migrate to this. And we're not done yet. We're still working on this. And next, I'd like to talk about a few challenges while working on this. The first challenge is testing. And the question is, with so many different services, how do we actually test them? This is challenging for us because we used to depend on manual QA process a lot. Whenever we ship a new feature, we ask QA to test that. And it's kind of straightforward and easy to do because we had a few clients and one backend API, and it's kind of straightforward to test everything working together. But in a microservice design, it's more complicated because we have so many different services, and it's much harder to test everything working together. So we try to solve these problems in a few ways, and the first is to enforce a very high unit test coverage. I mean, this is kind of common sense, but it's often forgotten. But this is extremely important in a microservice design because, before you try to test everything working together, you need to make sure each component of the whole system is working fine. And the next idea is to have automated test. And the idea is to have automated tests running, try to integrating different services and make sure that each feature is working fine by powering these services behind them. And if something is not working fine, the developers should be notified and try to fix them. And by doing this, we can largely reduce the manual QA process. And again, we need to do this because in the microservice design, it's just very difficult to manually test all the scenarios whenever you make a single change in each of the services. And the next challenge is the database. So if you remember, our existing API is in a data center called Sakura, and so is our database. So most of the data is in a data center in Hokkaido, but we're trying to run microservices in GCP, and GCP Japan happens to be in Tokyo, and it's not very close to Hokkaido. So how do we solve this problem? Well, first, the very first step is to run the DO layer services in Sakura, so that they can have direct DB access because they are in the same data center. But this is not ideal because in the future we still want to migrate to GCP, to utilize all the GCP provided services, for example, GKE and managed databases. So that's why we try step 2, which is migrating some of the database from Sakura to GCP. And this has been kind of work in progress, and we are starting from the kind of data that's kind of isolated from the rest of the system, so that we can, finish the migration without affecting the other part of the system. And actually, even with this, we can't really migrate everything because some of the data is just so big and not splitted, and it's just not supported by GCP. As you know, if you have your own database, if you have your own data center, your own physical machine, you can configure it with very high spec to support very high volume of data. And this is not easily available with a cloud service most of the time. And that's why we will try the third step, which is to create a Tokyo data center and host some of the databases and services in it. And the idea is to have the Tokyo data center act as kind of a middleman between the GCP data center, which is in Tokyo, and the existing data center in Hokkaido. The next challenge is transactions and locking. This is something we can easily write in a monolithic design. And this is obviously pseudocode, but basically the idea is, you start a DB transaction, and then you get some lock, and by lock I mean essentially select for update in a MySQL database, and then you start your heavy processing of the transaction. You try to update this table, that table, and send some notification. And if everything goes well, you commit the change. And if not, you roll back. Well, this is kind of easy to do in a monolithic design, but it's actually very difficult in a microservice design, because in the microservice design, each service should be responsible for their own database, which also means you're not supposed to have direct access to the tables of other services. So you can't directly, get the lock of some other table and update, some tables of some other services. So to solve this problem, first we are trying to introduce distributed locking for the locking part. And the idea is to use things like red lock to share locking mechanism across different services. And next, we're trying to refactor the whole transaction with asynchronous design. For example, using PubSub to move the transaction, to move some part of the transactions out of the transaction and do them asynchronously. And in this example, when you're updating these things, sending the notification is probably not necessarily to be done in that transaction. You can still update this data and maybe send the notification a few seconds later, which is fine. And another benefit of doing this asynchronously is that you can actually introduce better retry logic to ensure that this can be finally finished without having to roll back everything if anything goes wrong. And the idea of this is to ensure eventual consistency, because in the end of the day, what user cares is it actually worked. And in most of the scenarios, it doesn't have to be done in that 0.0005 seconds. It can be done in 0.1 millisecond. And this is kind of just the brief idea, and my colleagues will talk more about this in details with more examples. And that's all I had. Thank you.